4.5 Day 10 Notes, talking about the number that is E. So, E is actually, it's an irrational number. You can actually find it in your calculator pretty easy. If you look at the divide button over here, that's actually just second E. I hit enter, I actually get a value for it. So it's just a number. We're going to use 5 decimal places, 2.71828. That's good enough for us, but that decimal goes on forever with a bunch of different numbers, so it keeps going, just like pi actually. So we're going to use about 2.71828. That's good enough for us. E is an irrational number. And the reason we talk about it in this section is because it was actually found or constructed, created by someone who was studying interest that was compounded continuously. So not like monthly or daily, but if you keep going even more specific, like by the second, or even more specific, it gets really close to this value, and that's where you get all these decimal places. So it has to do with interest that's compounded continuously. That's where this number E comes from. Page 170 in your book actually gives a really good illustration of how the number came about. So graphically, how does this look? We're going to use this for an exponential equation. So y equals e to the x. So we actually know a lot about graphing exponentials. For this one, the a value, the starting amount, would be 1. Like the coefficient out here, there's nothing there, so that's 1. And the base b, well, that's 2.71828, right? That's what we approximate it to be. So this would definitely be exponential growth. So I can go ahead and put starting values at 1, and this is going to model exponential growth. So I'll keep my graph like that. So that's y equals e to the x. And then let's compare it to y equals 2 to the x. So again, for something like this, the starting value would be 1. So they'll intersect at the y-intercept here at 1. And then obviously the b value, the growth factor, is 2. So the growth factor here would be less than this growth factor. So when we go to graph it, it'll actually be underneath this graph in quadrant 1 because it's not increasing quite as rapidly. So that would be y equals 2 to the x in red here, because it has a growth factor that's a little bit less than e, which is 2.71828. And then how about y equals 3 to the x? So its growth factor is 3, so it's definitely more than y equals e to the x, that growth factor. So it's going to be a little bit above here in quadrant 1. But notice it goes below once you get back here because they cross at the y-intercept. So it's got a greater growth factor, so it increases more rapidly. So it's above here in quadrant 1. So that's a good comparison. E 2.71828. So y equals 2 to the x is a little bit below it in quadrant 1 because it doesn't increase quite as rapidly. And then 3 to the x is a little bit above it in quadrant 1 because it increases more rapidly because of that b value. And for all 3 of these graphs, they're all exponential. So y equals 3 to the x, y equals e to the x, y equals 2 to the x. For all 3 of them, they have the same horizontal asymptote, so they're all approaching the same thing. Right here on the x-axis, that's the line y equals 0. So they all 3 have a horizontal asymptote at y equals 0. So what does it mean to be compounded continuously? That's where this number E comes from. So now I'm going to give you a new formula. We've already done compound interest, but when you see this word continuously, that means we're going to use E. So continuously. That means E should be involved. So that's y equals A times e to the kt. So the exponent on e is k times t. So this does look really similar to exponential functions that we learned before, where it was y equals a b to the t. So this value e to the k, that's like your growth factor. That's like your b value. What is k? What do I plug in for k? Well, that's just like your interest rate or your growth rate as a percent. Right? And if it's given as a percent, we need to write it as a decimal. So k, when you write it, needs to be as a decimal, and that can be either positive or negative. And if this is really throwing you, like, wait, that's not the continuous interest formula I learned before, that's the same as the PERT formula. So if you prefer to look at it like this, like the balance in your account, B, is PE to the RT, that's really the same thing. The principal, that's the initial investment, E to the rate times time, that really represents the same thing. So that the PERT formula might be the one you're used to. So let's look at the first example here. So you invest $100 at 12% annual interest for 1 year. So we're going to make a comparison. What's the account balance if compounded? Well, part A, I want to look at quarterly. So what would the account balance be if it was compounded quarterly for 1 year, 12% annual interest, and the initial investment is $100? So let's go ahead and plug it into the compound interest equation. We have $100 to start with, and then we do 1 plus the rate, 12%, so that's 0.12. And this is actually our nominal rate. So what we plug in for R down here, that's the nominal rate. Remember, that's in name only. So that's like in the name of the problem. That's like your basic starting interest rate. So that's 0.12 divided by 4 because it's quarterly, so 4 times a year. And then the exponent, N is 4, and then there's 1 year, so we calculate this to be 100 times 1.2550881. And again, that was the nominal rate, 12%. But notice, we actually earn a little bit more than the nominal rate. So the fact that it got compounded quarterly, that's our effective annual yield. We can calculate our effective annual yield to be a little bit more than 12%. In fact, it's 12.550881%. So it's nice. The more you compound it, the more your effective rate is going to be. Then let's answer the question. The account balance is about $112.55. Okay, well, now that we just learned about compounding continuously, let's see what happens when we do this compounding continuously. So the balance is going to be the initial investment, so that's $100. And then we need E to the KT, or E to the RT, either one. So E, and the rate is 12%, so that's 0.12, and then the time is 1 year. So what are we really multiplying 100 by here? E to the 0.12. Again, you can calculate that easily in your calculator. So that's 100 times 1.274964, about. I had to round that number off. And just to show you a little bit of a shortcut with your calculator, it already has an e to the exponent feature. So if you just hit second ln, ln is right here next to the 4. So if you hit second ln, it already sets up e to a certain power. So then you can just plug in the exponent. In our case, we just did 0.12. So that's how I got that decimal. That's actually our growth factor. So now I just want to make a quick comparison. Which one's better? Which one earns more interest? The quarterly or the continuously? Well, compare the effective annual yield between each one. So this one, the E, the effective annual yield, how much bigger is it than 1? Well, 12.749684%. So it's got a little better effective annual yield, even though it started out with a nominal interest rate of 12%. And when you multiply it by 100, it's about $112.75. So believe it or not, the more you compound something, the more interest you earn. So it seems like compounding continuously is about as good as you can get. If you think about it, like every minute, every hour, every second of the day, the interest would be actually compounding. All right, second example. Give the continuous growth rate of each function and then graph each function. Continuous growth rate and then graph each one. So here are our functions. P equals 5 times e to the 0.2t. Q equals 5 times e to the 0.3t. And R equals 5 times e to the negative 0.2t. Okay, so I bring up this term, continuous growth rate. Continuous growth rate. That's important. So that really is just like the R value. So R equals 20% in this case because it was 0.2. In this case, the continuous growth rate, 30%. So that's really just like what we plugged in to be the coefficient on t here. In this one, it's negative 0.2, so the rate is actually negative 20%. So those are our continuous growth rates for each one. I really just looked at the exponent and looked at the value that was on t and wrote it as a percentage. Okay, so when it comes to graphing these things, I want to kind of picture them as just exponential functions. So if you can just tell me what the a value is and the b value, I can make a really good sketch. So it turns out the a value for all these is the same. You look at the first number there, it's 5 for each one. So if I'm going to graph it as an exponential function, each one has an a value of 5. So I know the y-intercept for all three of these graphs. I can go ahead and put that down in my sketch here. That's going to happen at 5. Okay, so now just compare between the three. I need to know what the b value would be. So what would the growth factor be for each of these? Well, for the first one here, if I can just zoom in on e to the 0.2, that would tell me what b was. So e to the 0.2, if I can find that, that'll be exactly what I need for the b value. So b is e to the 0.2, so I need an actual number for that. I need an estimate. So I can calculate that 3 decimal places, 1.221. So then that would definitely be exponential growth. Like this function you could think of as y equals 5 times 1.221 to the x. Okay, and then for q here, so its b value, if we think about e to the 0.3 here, I get 1.350 if I round to 3 decimal places. So another exponential function. Notice b value is a little bit bigger for this one, which should make sense. And then r, so if I zoom in on e to the negative 0.2, that's really just 1 over e to the positive 0.2. So my b value is 0.135. So this is definitely exponential decay. Okay, so I'm going to start with P here. I'm going to sketch that in purple. So P, I'm just going to sketch exponential growth, goes through 5 in the y-intercept. That's in purple. So Q, though, it grows a little quicker. So I'm going to make sure it grows faster, it grows a little sharper. It's above P, it's above the purple line when I go to make that. And then they cross at the y-intercept. So it'll actually be below the purple line down here. So then Q, I'll add that in green. Go ahead and label these too. So Q, a little bit bigger B value, and I had to calculate that to know that. So it's a little steeper than P. And then R, that's my exponential decay. So that's going to start over here and decay. But it's still going to go through 5 on the y-intercept. So R, that's going to be in like the brownish orangish color there. That's exponential decay. I'm just making a rough sketch here. That's my graph for R. So this is a decent sketch, and I was able to make it just because I knew the y-intercept for all three of them was the same. And then I could just compare the B values to see which one has a steeper increase or which ones are exponential growth, these two, versus this one that's exponential decay. And then one thing I want to note, again, is the asymptote. All three of these, even the decay, they're approaching the line y equals 0. So they all have the same asymptote, y equals 0. And if you want another illustration or some more explanation on this one, this is an example on page 169 of your textbook. All right, final example for these notes, example 3. I'm going to start you off with an equation. It's just q equals 2 to the t. So this equation shows how the quantity q is changing over time, t. So how q is changing over time, t. And I didn't tell you what t was. I didn't give you any units for it. I didn't really tell you what q was. It's just some quantity. So I have a few questions about this. First one, part A. What's the quantity at time t equals 0? Well, that should be pretty simple. You take this equation, you plug 0 in for t, right? So 2 to the 0, we know anything to the 0 power is just 1. So that would be like the y-intercept on the graph. But we can say the quantity q sub 0, or q naught, equals 1. So that's a little bit newer notation. Q sub 0, that's like q at time 0 equals 1. It's also like the y-intercept. Part B. Is the quantity increasing or decreasing over time? Hopefully you can tell just by kind of looking at it. Like the initial value be 1, the a value be 1, but it comes down to what the b value is. So the base is 2, or the b value is 2. And since that's greater than 1, we know the quantity is actually increasing over time. So this is definitely exponential growth. It's increasing over time because the base b is bigger than 1. In fact, the fact that b is bigger than 1, like b equals 2, that means the quantity is actually doubling, like the pennies that we looked at. The quantity doubles for each unit of time. I didn't say what it was. It could be weeks, could be months, could be years, but it doubles per each unit of time. I want to make sure and use that notation and that wording because that's what our book uses. And then part C. So what is the percent per unit time growth rate? So if that was years, you could think of it as what's the percent per year growth rate. But we're just going to keep it more general. We're going to say what is the percent per unit time growth rate? Okay, so we know the growth factor is 2. So at what rate is that increasing? The base, which is b, that's 2. So that's 1 plus 1. So you can think about it as like 1 is 100%, and you add 1 more, that's like your R, that's like your growth rate. So really, that's really 100% growth per unit time. So we can say our growth rate is 100% per unit time, which in this case is just another fancy way to say it doubles for every unit time. Like the growth rate is 100% per unit time. And then the last question here, part D. Is the growth rate continuous? So Q equals 2 to the T, is that continuous? And the answer you should answer, you should be able to come up with it right away. That's no. So notice there's not any E's in this equation, so it's not continuous. To be continuous, we're looking for something that has like a base of E raised to an exponent. So this is definitely not continuous. All right, that's all for these notes. I'll see you in class.